Alright, so I've kind of been talking about this a little bit throughout the other videos, and I didn't want to get into it until now. But I've been mentioning this idea of resonance structures, or this molecule has resonance. So we're going to get into that in this video, as well as we're going to talk about some exceptions that exist when you're drawing Lewis dot diagrams. So one of the examples we did was nitrate. And if you recall, nitrate had a double bond between one of the oxygens and then a single bond with the other ones. And I mentioned at the time that it didn't matter which oxygen you had the double bond to. And so I think in the video, actually, I had the double bond between this oxygen over on the left. But I said some of you may have done it in the middle, some of you may have done it on the right. And at the time, it didn't matter. Well, now it does matter. And so sometimes you can have molecules that exhibit resonance. And resonance occurs when bonding cannot be shown with only one Lewis dot structure. For example, this Lewis dot structure right here is only showing a third of what's really going on. So, for example, like I said, the double bond's here in the middle, but it could have been to the left and it could have been to the right. Now, here's the thing with resonance structures. The weird thing is, it's not that, okay, some structures have the double bond in the middle, where some structures in nature have it on the left or have it on the right. The reality is, you actually have all three of these structures existing at the exact same time. So the nitrate ion, the Lewis structure of it anyways, actually is it's all three of these that are happening at the exact same time. And the best example I can give is take, for example, I'm gonna choose a hopeful analogy that will make sense. Take, for instance, a golden doodle. They're cute dogs. You know, if you've never seen one, Google it. It's pretty cute, whatever. Well, anyway, a golden doodle it's a golden retriever and a poodle. But you can't say that it's a golden retriever because that's obviously only half the picture. And you can't say it's a poodle because that's only half the picture. And you can't even say that, well, sometimes it's a golden retriever, sometimes it's a poodle. It's a golden doodle. It's all of it at the same time. That's kind of a weird analogy, but in the same way, this structure of nitrate, it's not accurate to just say that this is the structure of nitrate. And it's even not accurate to say, okay, sometimes it's this structure, sometimes it's this structure, and sometimes it's this structure. No, it's always these three structures at the exact same time. That was meant to underline, not cross it out. Clearly I have issues. But it kind of goes along the lines of the fact, once again, that electrons are weird. Electrons are always all over the place, and they can be in multiple places at the same time, and they're unpredictable. So resonance structures show all of those possibilities as being wrapped up in one structure. So from here on out, you need to be able to spot resonance structures, and you need to show them. So if I asked you on an exam or a quiz or whatever to draw the Lewis structure for the nitrate ion, if you just drew this up here, you're not going to get it 100% correct. You will get points marked off because that is not correct. You have to show all of the structures because, and once again, I want to stress, it's not because, oh, these are all the possibilities. No, that's all happening at the exact same time. Notice we distinguish between them with a double-headed arrow. So you need to draw that double-headed arrow in between all your resonance structures. Now, nitrate had three resonance structures. Sometimes you're going to have molecules that have more than three. Sometimes they'll have only two. It really just depends. And some molecules have no resonance. Some molecules, there's just one. Now, resonance actually can be more, it can go further in depth. That's something you'll cover in organic chemistry should you have to. For right now, we're going to stick to the easy ways to spot resonance. And that is, if you draw a double bond or a triple bond, and it could be drawn in other ways, that's how you'll know it has resonance. For example, like when you drew this one, you said, hey, I could have put the double bond here or here. That's how you'll know that you have resonance. Okay, so we're going to get into more of that, but let's talk about some of the exceptions to the octet rule. So there's actually three exceptions. The first exception is you can have the central atom that has fewer than 8 valence electrons, and this is just due to an electron shortage. We've actually already started talking about this a little bit. For example, one of the exceptions was hydrogen. Hydrogen, remember, is happy with 2 valence electrons. It doesn't need 8. Helium is another one. Boron is one that you'll need to be aware of. Boron is actually happy with 6 valence electrons. So for example, I have BF3 here. So boron's the central, fluorine is the terminal, and so we've got 3 of them. Total valence electrons, boron has 3, fluorine has 7, but you have 3 of them, so that's 21. And so we have 24 valence electrons total. 2, 4, 6. Okay, so that brings me down to 18. And then if I take care of all my fluorines, there's 2, 4, 6, 8, 10, 12, 14, 16, 18. So I don't have any electrons left over. So at this point, you may see, oh no, boron only has 6, so I'm going to have to do a double bond somewhere. First of all, no. Remember, halogens, when they're in the terminal position, they don't want double bonds, they don't want triple bonds, they want single bonds. That's all they can do when they're in the terminal position. So they can't have double bonds. But also, boron actually is happy with 6. So even though it doesn't have 8, it's happy. This actually is the structure for BF3. So that's one of the exceptions. The other exception is you can have the central atom have fewer than 8 valence electrons, and this is due to there being an odd number of electrons. Okay, so this is going to be known as radicals. So let's look at NO2, and specifically it's the nitrogen part of NO2. So you have nitrogen that's in the center, 2 oxygens that are on the outside. Nitrogen has 5 valence electrons, oxygen has 6, but there's 2 of them, so that's 12. So 17 valence electrons total. Already you can tell this is going to be some nastiness. But let's take a look. Okay, we have single bond, that's 4 electrons, so that's down to 13. Take care of the oxygens, that's 2, 4, 6, 8, 10, 12. So I have 1 electron left over. Regardless of how many that you have, stick it on the central. There's the 1 electron. I'm done. 0. Now, oxygens are good. They have 8. Nitrogen is definitely not good. It has 2, 4, 5. It has 5 electrons. There is no way you're going to get this nitrogen to have 8. It's just not possible. You can't do it. However, we can get it as close to 8 as possible. Okay, we can do some manipulating to try to get that nitrogen a little happier, although we'll never fully satisfy it. So what I'll do is I'll take these electrons that are right here, just because I drew them really poorly. So I'll take them off, and I'm going to move them into a double bond. So now nitrogen has 7 valence electrons. I can't do that again because otherwise nitrogen will have more than 8, and that's not allowed. So this is the structure for NO2 nitrogen dioxide. Now a couple things. Number 1, notice the single electron. This is what makes it a free radical, or sometimes we just say a radical. That makes it extremely reactive. It does not like that. It's very unstable. So it's going to react very quickly to other things because it doesn't want that. But the other thing is this. Notice, why did I have to do the double bond here? Couldn't I have done it over here? So that is where you know you have resonance. So what I'm going to do is I'm going to do that double bonded arrow, and I'm going to redraw this, but now I'm going to put the double bond on the other side. Once you have one structure drawn, it should be easy to draw the resonance forms because you're just flipping things around. Just make sure that you don't go too fast. You want to make sure that you get the right number of electrons on every substance. So you would have to draw resonance for this one. I'm never going to tell you on an exam, make sure you draw resonance because it's assumed. You have to draw resonance. You need to be able to spot that. So that's the second exception, is you can have odd number of electrons. The final exception is something that you will come into contact with a lot. And that is, you can have a central atom that actually has more than 8 valence electrons. This is called an expanded octet. Now, how do you know if an atom can have an expanded octet? Because, for example, I said back here, I said nitrogen cannot have more than 7. It has to be less than 8. So how do you know what can be more than 8? The central atom can have an expanded octet if the central atom is an element that is in row 3 or larger. So for example, that basically means row 1 elements, which means hydrogen and helium, those are not options, and row 2 elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Those 10 elements, they cannot have expanded octets. Every other element on the periodic table can. So for example, sulfur in sulfur hexafluoride is going to look something like this. You got sulfur bonded to 6 fluorines. Now all these fluorines would have lone pairs. I'm not going to draw them for time's sake, but they all have lone pairs. But the key thing I want you to see is you're like, what the heck? How can sulfur have 6 fluorines bonded to it? In other words, it has 12 valence electrons. Like, how is that even possible? Well, sulfur is right here. It's in row 3. So it is available to have an expanded octet. So that can happen. Xenon tetrafluoride is another one. That actually can't. And actually, let me do this one real quick. And I mean really quick, because hopefully by now you're feeling comfortable drawing Lewis dot diagrams. So you know you're going to have 4 fluorines bonded to this xenon. So far you're probably thinking, well, that's not a violation, 8, but I've got to actually make sure I draw all my electrons. Xenon has 8. And you're probably thinking, wait, I didn't think noble gases can bond. They can. It is possible, especially the ones that are further down here towards the bottom. Helium, neon, and argon, those really aren't going to bond because they don't have space. We'll talk about that in Chapter 7 or Topic 7. But the ones that are further down at krypton, xenon, those actually can. So xenon has 8. Fluorine has 7, but there's 4 of them. So 7 times 4 is 28. So I have 36 electrons. I just took care of 2, 4, 6, 8 by bonding those fluorines, and so I'm down to 28 valence electrons. Fluorines are all going to have 6 each, so there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. So I have 4 electrons left. Oh gosh, I don't know what just happened there. Pen got a little crazy. I have 4 electrons left over after I do that. What do the rules state that I need to do when I have leftover electrons, but my terminal atoms are all good? Doesn't matter how many you have, 2, 4, a gajillion, even though that would never happen, stick them on the central. So I do it just like that. How the heck can you have 2, 4, 6, 8, 10, 12 electrons around xenon? It's because xenon is in row 5. It is available for an expanded octet. It can do that. So it is allowed. You'll see the expanded octet quite a bit. So just be aware of knowing that if the element is in row 3 or higher, it is allowed to have an expanded octet. Now, why the heck would you have an expanded octet? Well, we're actually going to cover that in the next video, which is looking at some more practice with the Lewis dot. So go ahead and actually this is for your own practice. Pause the video, draw these Lewis structures, and then you can hit play to resume, and I'll have the answers waiting for you. Okay, so here's the answers. So the first one, notice that the exception there is the expanded octet. Antimony can have an expanded octet that allows all 5 fluorines to bond. For the second one, the exception there is that it does have fewer than 8, and that's because boron is happy with 6. So notice there. And then finally, the last one is an exception, fewer than 8 as well, but that's because of the odd number. That's your radical. Notice there is resonance there as well, because the double bond there on one sulfur can be double bonded to either one, and actually they both are double bonded at the same time. That's the weird thing about resonance, so we need to draw both of those. And notice NS2 is just like NO2, because sulfur and oxygen are both 6A elements. So there's one more video that we're going to make, and that's going to be kind of taking everything we've learned throughout this topic all together. So the last video is that you see for this topic is just going to be a couple examples to help us write the best Lewis dot structure for 2 particular ions.